we do that, probably talk about sound, which is how we arrange and organize sound is sort of what we hear as music. So, what is sound? All right, I'm going to steal the words out of the professor, I've heard. As I am speaking right now, my vocal cords, voice box, whatever, are vibrating air molecules somewhere around here. And that energy is being transferred to your ear. Now, the way air molecules move around is a little bit interesting. If you've ever seen the Newton's cradle, so people here, this guy goes up. When it slams down into this one, it's this ball at the end that moves up here. And all these guys in the middle stay put. So air molecules basically work the same way. It's very hard for one particular oxygen-nitrogen molecule to move very far before it hits something. So it's essentially just staying in the same place. Now, once it does that, it's being hit on again by this one over here because my voice box is just constantly punching the air molecules right next to it at a speed of maybe a few hundred times a second. And then this one at the end here is the one that's punching against your ear that many times per second, which is interpreted by your brain as a particular signal and type of sound. The dynamic range of the ear turns out to be about 20 to 28 kilohertz. So 20 times a second to 20,000 times a second. Pretty alright. And it turns out that A can be defined as 440 hertz. So 440 vibrations per second of an air molecule against your ear, we hear as an A. So white noise, as it turns out, if I just stack the board like that, it's very hard to tell what kind of pitch that is, because it not only has a 440 frequency, but also 439 and 441 and 442 and everything out there. All at similar amplitude, so that your ear can't really pick out one over the others. So, you don't really hear much of a pitch at all. For anything that isn't a drum, you're going to want to be able to control the pitch, the primary pitch that you hear pretty well. And it's easiest to explain how that happens with air columns and strings. So, not coincidentally, a lot of our instruments are woodwinds and strings. So the math, it turns out, works out to be the fundamental frequency at which something vibrates is the speed of the wave over twice the length of the thing it's vibrating over. So if this were a string and I were just waving it up and down, there would be waves going through it, and then they would sort of bounce back, and then they just add up and subtract from each other to something like this. These guys don't really move, and they're called antinodes, and this thing in the middle here moves up and down a lot, 440 times a second for A, and that is called a node. And when this happens, it's known as a standing wave, and this is the fundamental frequency of the string or air column that we've been vibrating. So this length here is L. So when you can get this type of ratio to be exact, that's what you get. And for an air column, that would be the speed of sound over the length of your tube, 2 times the length of your tube. For a string, that would be the speed of the wave on the string over 2 times the length of the string, where the speed of the wave on the string is its tension over its linear density, so mass over length. As it turns out, strings themselves are pretty weak. If you just try to pluck a rubber band, you'll know you don't get much of a sound out of it. For a violin, it's the back that does most of the vibration, that transfers energy to your ear that you hear as the violin. It's also why guitars need holes for this body to be hollow and have a lot of air to sort of bounce around inside of it and direct it to your ear a lot better than the strings would themselves. So, if we take a look at our little waveform again, we try to overlay it with something that's just a slightly different frequency, well, if they're very close to each other, they're not going to sound too good. So this A and this A sharp, if you've ever played those two on a piano, you know that that sounds awful. Same with the B, more or less. However, if we get far enough away so that they actually line up really well, waves are additive, so what we wind up with is something that looks a little bit like this. And I'll get back to that later, but if we cut the wavelength in half or double the frequency, it turns out 440 hertz to 880 hertz, we get something that's an octave up. So 2 times the frequency, 1 octave higher. If we go 3 times the frequency, that'll give us like a 1320 hertz. And that turns out to be the 5th above this one. 4 times, you get the A above that, and that makes sense, because 4 is twice 2, which is an A, which is twice 1, which is an A. 5 will give you the 3rd. 6 times will give you the 5th. 7 will give you the 7th, and 8 will again give you the octave again. So that looks like a way to get a lot of notes here, just by multiplying one frequency by a bunch of numbers. So anyways, this thing, even though it's combined, it's made of 2 waves combined, it sort of looks like this L here is the overall wavelength and the periodicity. So this waveform still repeats with, say, a frequency of 440, just like this one, but it looks different and it's going to sound a little bit different. And that's one of the ways we can tell different sorts of sounds that have the same pitch. The word for that is timbre, and turns out it's more macroscopic effects that affect that. By the way, timbre is how you know an oboe sounds like an oboe, and how Louis Armstrong sounds like Louis Armstrong. If we take our basic wave and then we just sort of look at a audio visualization of whatever instrument or voice we want, it'll just be something complicated and something complicated repeating. And it's these big effects here, little fluctuations in intensity and volume and imperfections and pitch. Those things also create a pattern that every time your ear hears it, once you've had enough experience, you'll go, oh yes, that is a clarinet. So the last thing I wanted to talk about was how you tune a piano, which is basically assigning frequency values to each of these notes in here. Well, we already know how we get the 5th. We multiply it by 3, and then we get any up here. That's pretty far away. Let's divide it by 2, because we can do that, to bring it back between our original ends. So that would make it 660. So what we've done is multiplied this A by 3 halves. Alright? If we keep getting fifths, keep wanting fifths above this, we'll just keep multiplying by 3 halves. So 5th above this will be the B over there. And you know what, let's divide it by 2 again, so that we can get to this B. That will give us 495. We'll multiply by 3 halves to get out to this F sharp, 743. Multiply by 3/4 to get the C sharp. Get rid of this for now. Which will be 557. And now you know how I'm getting these numbers, so I'll just put the rest of them in right now. 470, 509, 7, 595, 26, 60, 705, 43, 793, 835. Okay, so if we've done everything right, a 5th below this one is the last note that we've hit, which would be this D. So multiplying this by 3 halves should get us to the A. It doesn't. And if you're particularly mathematically astute, you might realize that what we've been doing is multiplying by powers of 3 and dividing by powers of 2 to say that we want something that is twice our original frequency. clean this up a little bit. Divide by the ones, and we'll move this guy over. So 3 to some power equals 2 to some power. That's not going to fly. So by the time, if we've been tuning exclusively in fifths, by the time we get up to here, we have quite a discrepancy. It's sharp by a whole 12 hertz. I don't know how many cents that is, but it's definitely going to be noticeable. And this problem happens with if you tune by every or any interval that you can choose from here and onwards. So the modern solution to this is to say, all right, well, each note, to get a step that sounds constant, you have to multiply the frequency of the previous note by a constant. So, I mean, that's how we got fifths, right? Multiply by 3 halves. To get the fifth above that, we multiply by 3 halves. So, if we want to start at our original frequency, then we have to multiply it by a constant. There are 12 notes here, so 12 times to get twice our original frequency. That means our constant has to be the 12th root of 2. Let's see what happens when we do that. Start with 440 to 466. And there are a few things you might notice. One, these numbers do not line up. They're not exactly the same. 2, the difference between here and there is not constant. It's changing. So, for example, there's a difference of 4 hertz here, but for the very next half step, there is a difference of 1 hertz. And then for this one, there's a difference of 6. So, each of these intervals is not a constant above the last one. 730, 784, 831. Ooh. Guess what we get when we multiply this by the 12th root of 2? Well, obviously 880, because that's how we defined it. And the last thing that you might notice, or might not, that I might notice, is that this is how we define a perfect fifth. You multiply your original frequency by 3 halves. This is what we get when we multiply by 5 12th roots of 2. They're very close, but they're not the same. And that means the fifth on a piano scale is going to be slightly flat. Same is true for the other intervals. They will be a little lower or a little higher, but they will never be in tune. So basically, what you've done when you call a piano tuner over is you're paying him to make every single interval except for the octave out of tune.
All right.